Hi all, so in this integration by parts example, we're going to be looking at the antiderivative of x cubed over the square root of 1 plus x squared. So there's two big things I want us to pay attention to in this example. The first thing is, beyond choosing something to be u and something to be dv, when we actually integrate that dv aspect, we're going to get to use a substitution method to actually make that antiderivative of dv feasible. The second thing is, well, when we actually do make that choice of u and the choice of dv, we have to be somewhat thoughtful and thinking ahead to why are we making that choice. So on that note, let's actually begin there. So for this integral of x cubed over the square root of 1 plus x squared, really when we're doing integration by parts, we're thinking about that integrand as a product of two things. So we can think about this either being the product of, say, something like x cubed over the square root of 1 plus x squared. Or we could think about this as being x squared times x over the square root of 1 plus x squared. Or the third way, we could even think about this as x times, well, x squared over the square root of 1 plus x squared. So there's many different ways we could view that integrand. And really, if we choose one of these three ways, well, that kind of gives us some idea of what we call u, what we call dv. So for example, let's just see what happens when we make the wrong choice. So we're going to go ahead and make the first choice here, breaking up our integral or thinking about that integrand as a product of x cubed and 1 over the square root of x squared, 1 plus x squared. So as a spoiler, this won't work. But let's see what happens. So we think about this integral now as x cubed times the 1 over the square root of 1 plus x squared. And remember, we get to choose something to differentiate, that is our u, something to anti-differentiate, that's our dv aspect. And typically what we like doing is calling things that are polynomial the part that we differentiate. Just because whenever we differentiate that, we know the powers or the order is going to keep reducing closer and closer to just constants. So if we make that choice of u as x cubed, our du dx, well, that just gives us a nice 3x squared. And of course, you know, du then is 3x squared dx. Well, that means everything else under that integrand or in that indefinite integral is our dv. So in this case, that means dv would be, well, 1 over the square root of 1 plus x squared times dx. And well, when we actually go ahead and try to find, well, what is v when we do the antiderivative? I don't know about you, but that antiderivative is something that I just don't know how to compute. I don't know how to do a U-Substitution. If we let u equal 1 plus x squared, we're going to get a 2x kind of floating around through that substitution technique. We don't have any other method really to try finding the antiderivative right now. That's a hard antiderivative. So at this point, I'm basically stuck. And now what that means is, well, this particular choice of u and dv could have just been the incorrect choice to make for integration by parts. So actually, we're going to move away from that choice of u and dv and see if we can think about a possible other alternative to actually go ahead and compute our integration by parts in this example. So what I'll try next is sort of this middle case. So this middle case looks like, well, we have that x squared times 1 over the square root of 1 plus x squared dx. We're going to continue our convention of letting that polynomial be the thing we like to differentiate. So u in this case would be x squared. Our du in this case is 2x dx, which means everything else from that indefinite integral is our dv. So dv in this case is equal to, well, x over the square root of 1 plus x squared dx. And now let's see what happens when we go ahead and try to compute that antiderivative for dv. And well, if we think about this for a second, this actually can be found using U-substitution. So this is what I meant by the first kind of step in this problem. We're going to get to use a substitution method to actually integrate that dv to find v by itself. Except since we've already used a u in this problem, even though we're going to proceed with a u substitution, we can let w be that substitution variable. So we could let w in this case be 1 plus x squared, which means that dw dx is equal to 2x. And if we go ahead and solve for that differential of dx in terms of dw, we would find that dx is equal to dw all over 2x. So let's see what happens if we put that into that integral. So our integral, we still have x from the original. Now it's over the square root of what we just called w. And then we have times dw all over 2 times x. And now, lo and behold, what we see happens is those x's cancel out. And the integral we get to compute now looks like the integral of 1 over square root of w. Of course, we have that 1/2 sitting out in front times dw. And now what I like to do whenever I see just a variable under a square root, cube root, whatever, is I like rewriting it sort of in the more algebraic form. So this could be the integral of w to the minus 1/2 dw. And the reason I like doing that is because I know I can just use the antiderivative power rule to help us actually finish off that integral. So in this case, we have that 1/2 sitting out in front. We have w to the minus 1/2. We add 1 because of the antiderivative power rule, and we divide by that power plus 1 as well. And when we just do out a little bit of this algebra, this will be 1/2 sitting out in front times w to the 1/2, all divided by 1/2. So those factors of 1/2 in the numerator and denominator there cancel out. And what we finally find is that v is equal to w to the 1/2. And then going back to our substitution of what we call w, we know that w is actually equal to 1 plus x squared. So that antiderivative we were looking for v is the 1 plus x squared raised to the power of 1/2. So at this point, we have all of our characters we need to continue with the original integration by parts problem. We just got to do that kind of side calculation for figuring out what v is using that antiderivative that we computed using U-substitution, or in this case, W-substitution. So just continuing down here, let's put our u together. So our u from the original was x squared. We multiply that onto our v that we just found, which is the 1 plus x squared to the 1/2 power. And then we subtract off of that the integral of v, which is that 1 plus x squared to the 1/2 power. And then times du, which we found above, which was 2x dx. So if we just label everything here, this was our original u. That was the v that we found. That was the integral minus the integral of v and du. So those are all of our characters here, except since we still have that integral sitting there on the right-hand side, we're not done with this problem yet. We haven't computed the original function's antiderivative. So let's mosey on along. So we have this as x squared times 1 plus x squared raised to the 1/2 power. And the integral that we get to do at the end of the day, we can pull that 2 out in front. So we have minus 2 times the integral of x times 1 plus x squared raised to the power of 1/2 dx. And if we look at this integral on the right-hand side here for a little bit, we can see we can actually do this integral using U-substitution. And now in this problem already, we used a U, we used a V, we used a W. Let's use a Z now. So this will be kind of a, quote, Z substitution. So let's let Z equal 1 plus x squared, and then dz dx is equal to 2 times x. And when we go ahead and solve for dx in terms of dz, we find that dx is equal to dz all divided by 2 times x. And again, the reason why we let z in this case equal that 1 plus x squared, I know I glossed over this a moment ago, is because we know when we take that derivative of 1 plus x squared, we're going to get a 2x, or what's really important is we see that x to the first power in that derivative. So when we go ahead and divide by that, by switching those differentials, the dz for the dx, it's going to cancel out that factor of x that's sitting there out in front. So let's go ahead and make that substitution. So we have x squared times 1 plus x squared to the 1/2 minus 2 times the integral. That x is still sitting there, except now instead of 1 plus x squared, that's our z, still raised to the 1/2 power. And now instead of dx, we have that as dz all over 2 times x. And what we see happens is those 2's will cancel, as well as those x cancel for us as well. So what we finally have here is x squared times 1 plus x squared to the 1/2 minus the integral of z to the 1/2 power dz. And well, we have an integral that is just a variable raised to some power, where that power is not -1. So we can just use the antiderivative power rule, which means that antiderivative of z to the 1/2 will just be a z to the 1/2 plus 1, all divided by that 1/2 plus 1 in the denominator. And of course, since we're at the end, this is our plus, we get a plus c as well. So the last step that we get to do is, well, z isn't the variable that we want our antiderivative in terms of. We want to go back to the original with the original variable, which was x. So if we just remember, that was using this substitution where z was equal to 1 plus x squared. So anywhere there's a z in this antiderivative, we get to replace that with a 1 plus x squared. So finally, our antiderivative in this case is x squared times the quantity 1 plus x squared raised to the 1/2 power minus 1 plus x squared to the 3/2 power all over 3/2 plus c. And that would be our final antiderivative in this problem.